This is the first part of a multi-part series on modern, solid and testable ABAP code. The presentation was given in German at the betterCode event and is also available digitally in English. First, we will give a brief introduction and clarify what you can expect from this presentation. Then we will discuss the topic of patterns and various design patterns that we use in modern development. After that, we will take a closer look at ABAP Units and the various patterns and possibilities. Finally, we will discuss various tips that help with automating the system landscape. In the introduction, we want to address the question, why should we even bother with this topic anymore? The fundamental question is, why do we still write ABAP code today? The modern ABAP stack now consists of SAP Fiori elements for the user interfaces, data modeling via core data services, and AI support that helps us generate the various components. So why code it ourselves? Isn't ABAP actually obsolete? Let's take a closer look at the RAP stack. On the left, we see the entire data model. This basically consists of the table source, the core data services, additional content for value helps, and the actual service. At the view level, we have the actual Fiori application, which is responsible for the visualization. On the right, you'll find the behavior and its implementation, which in turn contains the controller logic. Here we're translating the data model into the MVC, Model View Controller concept. While this isn't 100% accurate, it offers a good approach to classifying the various components of the model. Therefore, the controller remains very important. Since we're using ABAP code here, ABAP Unit is essential for testability and readability. We should consistently use clean ABAP. We'll discuss this in more detail later. Furthermore, we should maintain a clear structure and encapsulation to prevent the ABAP code from becoming unwieldy. Nothing is worse than an action implementation that contains over 500 lines of code in a single method. For this, we need clean encapsulation and appropriate objects that meaningfully divide this logic. What can you actually expect from this presentation? Well, what you can't expect is basic training in ABAP OO or ABAP Unit. There are plenty of foundational courses that go much deeper into the details of the basics. However, you can expect to learn advanced techniques, such as various patterns and design patterns that we use to build testable code. Furthermore, you will receive an introduction to various approaches for creating and maintaining testable ABAP landscapes and regularly running automated tests. Let's therefore try to first delve into the different patterns. These are not all classic design patterns, but sometimes simply a certain way of using objects in the ABAP system. We always follow the same basic structure. We have a class that generates and stores a timestamp. The timestamp is made available as a public attribute after saving, so it can be used directly without having to use a corresponding getter or setter method. We will follow a chain of patterns that build upon each other, from the static class through the instance class to the interface definition, the factory method, and the factory itself. These patterns build upon each other in such a way that we will later get an overall impression of what has been specifically improved by each use. Finally, we will look at the singleton, a special way of defining and using an object. The static class is the simplest pattern you can use. You've created a class where all methods and attributes are statically defined. This is essentially a function group. It's not ideal design, as we lack true reusability in the sense of object-oriented programming, like inheritance or polymorphism. However, we've effectively encapsulated the logic cleanly within an object. The actual attribute, the timestamp, is set to read only. This ensures that we can read it from outside but cannot directly manipulate it. We leave the ability to change the value exclusively to the save_timestamp method. The get_timestamp method retrieves a current timestamp and returns it. We've created a separate class for its use, which you can also find in the demo material. Here we call the save_timestamp method, which retrieves a current timestamp and stores it in the class. We can read the timestamp via the public attribute and output it at the end. The catch is that the class isn't really flexible at the moment. Since it's static, we can't create independent instances, but always work with the same global state. So we can only store and process exactly one timestamp at a time. Next, we'll look at the instance. The only difference from the previous version is that all definitions that started with class data or class methods have now been replaced by simple data and methods statements. Otherwise, we don't need to make any changes, but this gives us much broader possibilities. In the next step, let's look at how to use the class. We can now, for example, create a table of the class type in which we store different instances. In our example, we do this 3 times. We create a new instance each time using the new operator, call the logic, and store the respective timestamp. We then add this instance to our table. We get a table with 3 instances, each containing different timestamps. With this, we have overcome the global state of the static class. As a first step, we create a new interface. An interface serves as a blueprint for a class. In this case, we can simply copy all the components of the class that were previously in the public section and don't need to make any further changes to the definition. We now implement this interface in a new class. The corresponding definitions can then be found in the public section. The method names change slightly as the interface name is now part of the method name. To access a public method of the interface, we must always go through it. In this case, we use an alias for access. This allows us to use a shorter syntax for an attribute from the interface. However, we would not generally recommend this approach without reservation, as it makes searching for the original element within the code more difficult. In the next step, we create a new class with an initially empty implementation. For this, we include the interface in the class. The methods remain without logic at this stage. This approach allows us to create several different implementations of a single interface. These all outwardly have the same interface, but exhibit different behavior in detail. How is all of this actually used? For this, we use an instance of the interface type and a table that holds various objects implementing the same interface. First, we instantiate the class with the interface for which we have a concrete implementation and append this object to the end of our instance table. In a further step, we can create an instance of the empty implementation in the same way. We can use the same variable to create the instances sequentially and add each one to the instance table. However, dealing with the different instances and interfaces presents a slight challenge. Since the interface defines the public interface, it primarily serves to work with the various objects, as all relevant methods and attributes are defined there. However, if we have an instance of the class type, we must explicitly access the interface, for example, to call a method like save_timestamp. This makes the call relatively long in the code. Alternatively, we could perform a cast. To do this, we define a reference variable of the interface type and assign the class object to it using a casting operator. While this shortens the actual method call, it requires the additional step of casting. Working with interfaces is therefore often a balancing act, as we either have to choose the long path via the interface components or ensure the corresponding target reference through a cast. The factory method is intended to solve the actual problem. We create a static create method that returns an object of the interface type as a result. This allows us to ensure that the correct type is returned and we no longer need to perform casting. In the class, we set the instantiation to private, so the class can only be created via the create method and no longer directly via the constructor. Furthermore, we have the option to perform preliminary work in the create method, calling additional methods after the instance has been created and, for example, performing initialization. The method is called create because it creates a new instance of the object and returns it to the caller. No further adjustments are necessary here. When using the factory method, we only need to bind the instance and can then, for example, use the method chaining functionality directly afterward. In a second example, we call the getTimestamp method directly after the instance has been created. We chain the method call to directly obtain a new timestamp without having to first store the instance locally in a variable. This chaining makes it relatively easy and manageable to use this object. The factory is intended to solve the actual problem of the factory method. With the conventional factory method, we often have the problem that we are still bound to the actual implementation of the class. This makes mocking the instance relatively difficult and replacing the actual implementation almost impossible. To solve this, we place the actual implementation in a private global class. This class is not intended to be used directly from outside, but is only accessed via the interface. The class instantiation is set to private. Since we don't provide a create method in the class itself to create the object, we use a global friend here. Through this friend reference, we authorize the actual factory class to create the object in the system. This doesn't change the rest of the implementation. The actual factory now takes over the create method, as we already know it from the factory method. The class creates an instance of our actual implementation and returns it as the interface type. We set the factory class itself to abstract so that no instances can be created from it. We also set the class to create private. This ensures that only the static create method can be called to create a new object. Direct access to or instantiation of the factory is therefore excluded, as this is not required. The usage and invocation are then very similar to the actual factory method, because we can also perform method chaining or have a new instance returned to us. The only difference is that we do not work directly with the implementation, but always use the factory to obtain an object. This decouples the caller from the concrete class or implementation. Let's take a closer look at the singleton pattern as the last one. The singleton, as the name suggests, is responsible for always returning exactly one instance, ensuring we always have the same instance. This helps us later during processing. We don't need to hold the instance in a local variable at runtime. Instead, we simply call the method repeatedly to obtain the exact same instance. However, this requires that we are in the same session. The difference from a factory method is that we don't have a create method here, but rather a method called get_instance. This returns an instance either to an interface or, as in this case, to the actual class, since we only have one implementation. Additionally, there is a static attribute that the singleton holds. The get_instance method first checks whether the singleton has already been created. If not, we create a new instance. Otherwise, we return the existing instance. This ensures that we are working with the same instance system-wide. In the example shown, we obtain an instance and store a timestamp in it. Then we create a new instance using the get_instance method, which is technically still the original instance. Now let's mistakenly assume that we have an empty instance. However, if we compare the two instances and their timestamps, we will find that they are exactly the same timestamp, even though we didn't execute a storage method on the second call. This is because we always receive the identical instance via the singleton pattern. This means that the change we made in the first step is already present in the second call. Therefore, the timestamps are identical. To better understand the patterns, let's look at them directly in the standard. We have selected some examples that already exist in the SAP standard. We are referencing an ABAP environment that runs in the cloud and provides corresponding APIs. We will now examine these various APIs in detail, define the different patterns on them, and take a close look at the respective implementation. We will very likely also encounter deviations that do not conform to the shown standard or usage. Let's first look at a static class. The class CL_ABAP_context_info is an important class because it provides us with information from system fields in ABAP Cloud, such as user data, system data, or times. If we look at the class in outline view, we notice that there are many types declared for external use, since it is an API. In this context, every method is also defined as static, which is why instantiation is not necessary. It is also noticeable that there is no constructor and therefore no instantiation is provided for. Basically, the class is still set to create public, meaning that instances could theoretically be created. The second class is an instance-based class for zipping binary files. In the outline, we find the constructor. This already makes it a very good representation of an instance class and shows that it is intended to be used as an instance. What we don't see is an interface. Therefore, no uniform interface or blueprint for creation has been defined. Certain attributes, such as constants that are publicly available, are static, but this is due to the nature of the constant type. Furthermore, there are many private methods intended for outsourcing coding and internal management. The third class is an implementation for an application job. This is evident primarily from the use of an interface to implement the individual methods. However, upon closer inspection of the specific implementations within the methods, we see that only rudimentary information is present. Since we are working with an interface implementation, we must fully implement each method of the interface within the class. This is particularly evident in the last method, which contains no actual executable code, but includes a pragma to indicate its necessity. Because the class includes the suffix base. Since the name contains a, we assume it's a basic implementation that's always used when no more specific implementation exists, which is why it's implemented empty here. The next class is a factory method. We can see this from the fact that we have a static create method with the exact same signature as the constructor. Instance creation has been set to private, so no instances can be created directly using the new operator. In the create method implementation, we see that we create a new object and pass the parameters one to one. We then return this object using the returning parameter. This creates an instance of the class, which is the typical use case for a factory method. In the next example, we'll look at a factory. We see that firstly, it already has the term factory in its name. Secondly, it again has a static method that creates the instances and a corresponding interface that handles the implementation. The create instance method creates instances of the class, in this case the current class itself. This means that if we look at the object more closely, we see a hybrid implementation of a factory method and an actual factory. Creation is also set to private here. Since the individual methods in the lower part are directly implemented, we can assume that this is actually a factory method and not, as the class name suggests, a factory. Therefore, it is particularly important to name objects correctly and use them according to their use case. Finally, let's look at the singleton. In this case, we have a class with a getContainer method. This method manages the corresponding singleton. In the private attributes, you will see a reference to the container type. This is our singleton instance. In the getContainer method, we always first check if the singleton has already been created. If not, we create a corresponding object using a factory, store it in the attribute, and from then on, only return this single instance. The class also has an initialize method, which allows us to reset the singleton, for example, to start a new processing cycle. However, two critical points stand out here. First, it's possible to mistakenly create another instance of the class, which makes no sense for a singleton. Secondly, the getContainer method name does not indicate that we will receive a singleton, but only uses the actual class name. Let's first take a look at ABAP Units and the question of why we should actually work with unit tests. On the one hand, we naturally have the option of not writing unit tests. However, this means that we have a very high manual effort to test and validate the various components every time. In a manual process, we would never test each individual component in isolation. This means that certain parts of our code would likely never or only rarely be tested. This creates the real risk of releasing untested code into production, which could later cause us serious problems. At the same time, code is not always changed by the same developer during the application's lifecycle. Should another colleague ever need to extend or modify our code, there is a certain reluctance and often a real fear of even touching this code without automated tests. Since the deeper relationships of complex components are not immediately apparent without test coverage, it is difficult to predict which dependencies might be damaged or affected by a change. The risk is high that problems will arise later in production because certain use cases simply could not be considered or automatically checked beforehand. On the other hand, we find the use of unit tests. This means we always have reliable validation against the expected result of a method and can thus see directly during development whether our implementation works correctly or not. At the same time, sufficient coverage with unit tests on our code provides us with a robust safety net. We can use this safety net to implement later changes or refactorings. The tests give us immediate feedback on whether the existing logic continues to work as desired or whether we have inadvertently introduced errors through the adjustments. This applies both to in-house development and to work done by third parties. Another crucial advantage is the increased change frequency. Since the time-consuming manual testing effort is eliminated, we can make significantly more adjustments to the source code in the same amount of time and release code in shorter cycles. The automated tests can ultimately be executed with just one click and within seconds. The third point deals primarily with testing specific scenarios and edge cases. For example, if we receive a bug report in production, we can replicate this exact scenario in a unit test. From this point on, the error will be automatically checked with every future change. In the future, we won't need to actively think about this specific case anymore, as our test cases are permanently based on the assumption that this exact problem won't recur. Nothing is more annoying in everyday development than a bug that has already been fixed, but reappears in production as a regression due to later code changes. This is precisely where unit tests demonstrate their strengths. The final aspect concerns the documentation of functionality. Unit tests serve as the best form of technical documentation for the use of code without creating any additional manual effort for document maintenance. A third developer looking at the test cases immediately sees how the code must be called, how the input parameters must be filled, how to handle the result and the return values. So what exactly do the tests look like? How should we structure them? And what number or test coverage is important? We should answer these questions for ourselves beforehand. Regarding the number of unit tests, it's important to ensure that we don't just write the so-called happy path, that is purely positive tests, but also, of course, cover negative scenarios. This means, how does our implementation behave when the interfaces are supplied with incorrect information? Additionally, we can define thresholds to check, for example, whether certain exceptions are thrown in the event of an impending overflow. This means that the majority of the method is structurally tested. As a minimum standard, the positive and negative baseline scenarios should always be covered, since validating all conceivable extreme values naturally increases the effort required to create unit tests. Furthermore, we should critically examine the quality of the actual tests. Code coverage is not the sole criterion for high quality. Much more importantly, our tests must be absolutely repeatable and independent of external influences, so they can be executed quickly, time and again, and obtain reliable results. The rule here is, individual tests must not run for too long. We want immediate, fast results. After all, a unit test is not a performance analysis. Additionally, we should use automated test suites to validate side effects on other source code and calling programs. Fundamentally, a single unit test is meant to check the actual isolated object. However, if all your rep business objects, CDS helper classes or processing logics have their own unit tests, you can run these tests regularly across all objects using the appropriate tools. Therefore, if we change types, interfaces, or the behavior of methods, the overall result immediately shows whether any utilizing components have unintentionally changed. This is especially helpful for the future and for the period before production deployment, allowing you to identify and fix errors early before they even reach production. Let's take a closer look at a scenario. In this case, we use the generated factory with the corresponding implementation, as we built it in our previous exercise. We then implement a new component that uses the factory, that is, our actual implementation, and want to write a unit test based on this new component. This simulates exactly the behavior when we provide our colleagues with a corresponding API that they can use in their own applications, while simultaneously ensuring that our components remain testable in isolation. Let's take a closer look at the classes. We again use the same interface that we defined earlier. We have an implementing class that is instantiated via a factory and creates a timestamp accordingly. Now we create the actual implementation of our class. This class has a public method that checks whether we have reached the right moment. If this is the case, we return ABAP_true, otherwise ABAP_false. In the actual implementation, we use the factory to generate our API. We retrieve the current timestamp via the timestamp object to compare it. We then return the result of this validation as the method's return value. This is a fairly simple function and something we wouldn't normally write for production, because the real problem is the right moment is extremely limited in time and almost impossible to hit exactly in reality, unless we were to work with a logical time period instead of a fixed timestamp. In the test class, we have already created the corresponding ABAP unit tests, including a positive and a negative test case. Once we reached the right moment and once we did not. Apart from that, we have a relatively simple implementation, which we will now execute in the unit test. To do this, we use code mining in the ABAP development tools, click the Run button and start the actual unit test. The test result currently shows the following. Our test case for the scenario where the moment was not reached works perfectly and is stable for testing. This is simply because we never actually hit the exact hard-coded moment in a standard test run. But this is precisely where the problem lies. We currently cannot deterministically test the positive test case that is supposed to check when the moment is successfully reached. Since the method always queries the actual current system timestamp internally, we have no control over the returned value in the unit test. We now want to remedy this lack of testability. To do this, we will extend our framework and the corresponding objects with a mocking capability. To solve this problem, we use the so-called Injector pattern. We haven't presented this design pattern before, but we're now implementing it specifically for this use case. In addition to the existing factory, we're extending our architecture with a so-called Injector class. This Injector class allows us to manipulate the instantiation in the factory at test runtime. The goal is not to receive the actual production implementation back at the end, but rather a test double defined by us. Conversely, this means we don't have to make any messy modifications or branches in the production code to enable the test scenario for the factory. This is perfectly in line with a modern, testable software architecture in the ABAP environment. In the next step, we create a so-called test double, or in this case, a local test double. since we are implementing it locally within our test class. To do this, we create a local class ltd_timestamp and define it with the addition for testing. The for testing is essential here because it signals to the runtime system that this class exists and may only be used in the test context. We then implement the interface that we also use in our production object. For this, we use the addition partially implemented. In ABAP, this addition ensures that we don't necessarily have to implement all methods of the interface in our local test class. Instead, we can specifically decide which methods we need for our specific test scenario. We see this immediately in the result. We can simply omit an unnecessary method and implement only the relevant get_timestamp method. Since we are in a controlled test scenario, we now have this method return precisely the predefined timestamp that we need to validate the successful test case. We have already created a corresponding injector for this use case, which you can also find in the package. This class is defined as abstract final so that no instance of it can be created. It has also been declared with the for testing addition. This means that the injector can only be called in unit tests and is not available in production code. This effectively protects the injector from other developers mistakenly using it in a production context to inject unwanted replacement instances into our factory. The injector has a static method for injecting the test double. This method receives the test double and stores it in the factory. Conversely, this also means that we need to make a small adjustment to the factory itself. In the global factory class, we have defined the injector as a global friend. This gives the injector class the right to access the factory's private attributes and methods. In the private section of the factory, we define a static attribute of the type of the corresponding interface. In this attribute, we will later store our actual test double at runtime. Finally, we adjust the create method of the factory. Here we first check if the test double is set. If so, we return the instance of the double. Otherwise, the normal production code is executed and the regular instance is created. To make the test double work, we call the injector before starting our unit test to prepare the instance within the factory for the test run. To do this, we call the inject method and pass a new instance of our local double, which we previously created as a local class. Of course, it is also possible to use the official test double framework, as it can also dynamically create test doubles. In this case, however, we solved it manually for better understanding by creating our own local implementation. This makes it directly and transparently visible in the code which values are returned. With the double framework test, we have to make corresponding pre-configurations, such as setting the expectations and response values, which means more lines of code and requires some explanation. Therefore, the integrated framework is not part of this presentation. Now, if we run our unit tests, we get a green result for both test cases. This means we are now able to test the scenario in which the right moment is reached. By replacing the actual implementation via the factory at test runtime, the application accesses our own implementation and returns precisely the value we defined. The crucial point is, this is possible without burdening the production code with messy test branches. Instead, we simply use the injector pattern as an additional, clean architectural tool for test-driven development in the ABAP environment. What important tool information can you find online that can help you improve your code, simplify your programming style, or even remove old code? You should especially check out the Clean ABAP Style Guide. This is a GitHub repository populated by the community that combines the most common programming pattern and best practices into a single document. There you'll find do's and don'ts to help you in your daily development. It explains which statements you should use, how they are structured, and what the best practices are for building object-oriented maintainable code. The document is relatively long. It's helpful to get a general overview first, perhaps read the entire document once and then refer back to it whenever you have questions or are unsure about something. Next, we recommend the ABAP Cleaner, a plugin for the ABAP development tools or Eclipse. With this plugin, you automatically receive a large number of rules that can format your source code directly after development. This allows you to quickly create simpler, standard-compliant code without having to invest significant effort in actual formatting. Essentially, the ABAP Cleaner works similarly to the Pretty Printer of the past, except that it performs even more formatting and automatically cleans up outdated statements or overly complex instructions. This saves you a great deal of time and energy when it comes to cleaning up source code. With a single keystroke, your source code is as clean as your colleagues. Variants and settings can be shared within teams. This way, you are not the only one using it. Everyone on the team uses the same variant, resulting in a consistent code appearance. This helps enormously with later maintenance, because code is read far more often than it is written. Consistently formatted code that is easily readable for everyone is ultimately very easy to maintain. Have you looked at the document and installed the ABAP Cleaner? Then there's also CodePal, an open source project for the ABAP test cockpit. With it, you can run additional checks in the system that verify whether your code also complies with the Clean ABAP style guide. This is incredibly useful if your team has committed to a common standard. This way, everything is checked again during the release process to ensure it meets the guidelines. Perhaps a colleague forgot the ABAP Cleaner or formatted something differently. Here, the ABAP test cockpit specifically helps to perform a final quality assurance check. Of course, build pipelines can also be built based on these variants. This way, code running into the test system is automatically checked, cleaned up if necessary, and only then deployed accordingly. A very exciting development of recent years is the integration of ADT Actions into the ABAP development tools. This gives you the ability to integrate your own IDE functionalities, or extend the IDE with specific automation techniques without leaving ABAP. Let's look, for example, at the previous section where we asked, why should you build a factory and an injector? Generally, it takes a relatively long time to implement these objects in the system. We have to create the interface, program the actual class, and set up both the factory and the injector. That's quite a few objects that we have to create manually, which in turn have relationships with each other, and therefore take a considerable amount of time before we can even begin the actual development. Since we developers are fortunately mostly lazy, we can of course automate this step. This doesn't necessarily have to be done with AI. It can also be done relatively heuristically with a simple structure and a corresponding generator. For this, you'll find MIA, My IDE Actions, an open source project that offers several standards. One example of this is the generation of classes and their dependencies. This allows you to automatically generate all the necessary classes and theoretically specify optionally if you don't want certain objects. After generation is complete, the framework even takes care of activating the objects for you, so you can start programming directly and save yourself the recurring work. We also had a section on unit tests and how to build and further automate them, for example by using injectors so that we no longer have to modify our actual source code. The same applies to regular tests. Once we've built the tests, we should definitely run them manually during development to repeatedly check whether our actual implementation is still working without errors. In most cases, this is limited to the local class with the actual implementation or, at most, to the package in which we are currently developing. The tests are quick to run and thus provide us with fast feedback, so we can continue working on them directly. The second pillar is to check when the transport is released. This means that the ABAP test cockpit can, for example, automatically execute and check all unit tests while we release the transport request. This is also available in the cloud as APIs, meaning we can integrate this step into build pipelines and have it automatically checked whether our code is still clean and the unit tests run without errors. A basic requirement for this, however, is that the tests are isolated and can be executed as efficiently as possible, without dependencies on the actual system. Then we have the topic of the automatic execution of unit tests. This means we regularly run unit tests on entire packages, or perhaps even the complete system to validate whether the system is still error-free or whether, for example, changes within the system have caused problems elsewhere. For instance, we might change an interface or structure, which in turn has no effect on our local tests because we have adapted and extended them accordingly. But perhaps someone else in their development uses exactly that structure, so their development would now encounter errors. Therefore, it makes perfect sense to regularly run unit tests beyond just one's own package to validate the entire system. For on-premise systems, there's the ABAP Unit Runner, a simple standard report that runs in the system and can be scheduled as a background job to automatically execute unit tests and send the results via email. Do you want to do this in BTP, for example, on a Steampunk system? There, you'll either need a build pipeline or you can use an open source project to trigger the automatic execution of unit tests and have the results sent to you via email. We generally recommend running the test regularly, for example once a day, to ensure that all unit tests in the system continue to run successfully. Here we have a comparison of both ABAP Unit runners, one for on-premise and private cloud environments and the other for the open source version for the public cloud. The standard ABAP Unit runner is started via a report, while the open source version runs as an application job since reports are no longer available in the cloud. You will find essentially the same or similar settings in both tools that you can use to schedule the job. In both versions, you can also enter an email address to receive information about the test run. The second screenshot compares the presentation of the test results. On one side, you'll find the email from the ABAP Unit runner with the corresponding results, and on the other side, the email summarizing the results of the runtimes and the executed tests. Generally, it's worthwhile to always run an ABAP Unit runner across the entire system to validate as many unit tests as possible, without having to invest a lot of manual effort in actual maintenance. Instead, you simply check regularly whether the entire system and the unit tests running within it are clean and functioning without errors. This brings us to the end of this entire series. Therefore, we want to summarize the 3 most important points once again. The importance of ABAP remains, even in the age of web and AI. A great deal of ABAP development will continue to be required to map the complete business logic within the system. Good design remains the responsibility of the developer. If clean structures are not established, both reusability and testability within the system will suffer. While AI can help automate, improve, and make unit tests more readable, the final decision should ultimately remain with the actual developer. We have looked at patterns, which are an important component of ABAP architecture in a system. Correct application and usage help you improve testability and achieve it without significant system modifications. We have shown the standard pattern that can be used in everyday practice to decouple code and package it into clean objects. The third point is testing. Unit tests should be the minimum standard for clean development. These help you to make later adjustments more quickly and have regular validations that help you extend code quickly. Regular tests running on the system help to check the entire system and identify and fix possible side effects as early as possible. Furthermore, even if testing is actually outsourced further in the process, tests help to accelerate the further development of the system. They provide a safety net for new developers, showing them how to read and extend the resources without fear of breaking anything. Therefore, thank you for your attention today and throughout this series. On the left, you will find the QR code to download various resources such as the presentation, materials, source code, and other articles used as references for this post. On the right, you'll find my LinkedIn profile if you'd like to connect, have further questions, or simply stay up to date with new articles and information. Therefore, thanks for watching and see you next time.